Okay guys, so in the last lecture we saw geometrical isomerism in case of double bonds, so or alkenes. So in this case, in this lecture we'll be seeing a new case, which is geometrical isomerism in case of cyclic compounds. Okay, so just let me write down the heading. So geometrical isomerism in cyclic compounds. Okay, I hope you remember the three conditions which I wrote in the last lecture about geometrical isomerism, that it has to be first stereoisomer, then it has to be uh, rotation restricted, and third, there has to be change in areal distances, difference in areal distances of substituted groups. Okay, so please remember these three. And now let's take some examples on the same. We have so what do I mean by a bond which is darkened and a bond which I show with simple dashes? So when I dark a bond, it just implies that this CH3 is towards your face. So right now you are seeing this on your computer screen or on your mobile screen. So this is you can consider the plane of your computer screen, which is the same plane of the cyclohexane ring, and these two CH3 groups are actually coming out of your computer screens. Okay, so when you say a compound with when you draw a compound with uh, darkened bond, it just means that it is in some heightened plane, or it is coming on your face. You can just imagine for now that it's coming on your face, right? So it's not in the same plane as a cyclopropane ring. And when I see this when I draw this dash across the CS3, this means that it is going away from your face, or it is uh, expanding itself within the computer screen. Okay, so it's engrossing within the computer screen and it is away from your face. So the computer screen is in the same plane as your cyclopropane ring. Okay, so with this I think this is a stereoisomer. This is rotation restricted as it is a ring, and the aerial distance, the difference of aerial distance is also there, because in this case the aerial distance is just this, but in this case this is actually coming towards your face and this is actually going away from your face. So the L2 distance would be greater than L1 distance, and as a result this is showing geometrical isomerism. Okay, let me compare this. And this, is it showing geometrical isomerism? Yes, because the distance between these two which are facing towards your face will be L1, and this distance would be obviously lesser than this distance, because CS3 is towards your face, CS3 is away from, and this CS3 is away from your face. So you can see that there is L2 is greater than L1, hence this is showing geometrical isomerism. Third example is this compound showing geometrical isomerism? No. Why? Because there are similar groups attached on the carbon atom, hence this is not in geometrical isomerism. So can this compound show geometrical isomerism? Yes. Why? Because in one case I can draw CS3 towards my face, and in this case away from my face, and the second compound I can draw in which both the CS3s are towards my face, CS3 and CS3. Let us see if geometrical isomerism is available can be found in this Yes. Why? I can change the position of Cl, hydrogen, so there will be difference of aerial distance between the bulky groups. So this is in geometrical isomerism. Okay, let us see for this. Is it in geometrical isomerism? No, because the most bulky group that is attached to this is the same ring which I can get from the same this. So both the compounds on both the alkenes are same, substituted with the same carbon atoms, hence it will not show geometrical isomerism. Seventh example would be, is geometrical isomerism there in between these two compounds? No. Why? Why geometrical isomerism is not there between these two compounds? Because if you look at the ring, the positions of these carbon atoms will be fixed related to this and this carbon atoms, right? So if you go anti-clockwise or you go clockwise, there is same set of or same group attached to this carbon atom, which is these carbon atoms, and if you go clockwise, then also there is a set of same carbon atoms which is attached to this carbon atom, and the relative position will not change forever because this is a compact ring, this is a closed ring, hence the positions of these two substituents is not going to be changed, hence this will not show geometrical isomerism. What about this compound? Will it show geometrical isomerism? Yes, because I have just drawn one picture of the coin, or one part of the coin. You can actually also draw another picture in which you can come up with this structure. So this is in geometrical isomerism. Okay, and why this is in geometrical isomerism? Because in one side of this carbon bond and on the other side, the configuration of this carbon atom is changing. Previously it was towards my face, now it is away from my face. Okay, now let us take an example with this. Is it in isomerism, geometrical isomerism? Yes. Now let us take this example. So in this example we have something like hydrogen attached here, and here. Okay, so in both the cases, as you can see that in this case you have hydrogen atom attached here and second hydrogen atom attached here, but in this case you can have both the hydrogen atoms attached on the same side. So this is trans and this is cis, hence these both are in geometrical isomerism. Okay, so let's take the last example. This is a 8-member ring. This is not aniline. Aniline has to be have all the conjugate pi bonds has to be there, the tub shaped structure. This is not it. And another is this is a twisted aniline in which actually this bond is actually going out of the page or out of the plane or inside the plane, and this is coming from okay, so this is a twisted form of aniline in which you can see it is a trans aniline because the hydrogen atoms are attached here, and this is a cis not aniline, cyclooctane. or cyclooctene. Okay, so now let us get into what is known as cumulene. So I'll just write the topic. So cumulene. So cumulene also shows geometrical isomerism, and we'll look into as to why it shows geometrical isomerism. So what is cumulene? So if there are two or more carbons that are directly attached with pi bond, then it is known as cumulene, and the smallest cumulene is known as allene. So by the definition, if two or more carbons are directly attached with pi bond, then it is known as cumulene, and the smallest cumulene is allene. Okay, so if the number of pi bonds are even in cumulene, then the terminal carbon valencies are perpendicular to each other, and it will not show geometrical isomerism. So I'll write it like, if number of pi bonds are even in cumulene, then terminal carbon valencies are perpendicular to each other, and it will not show geometrical isomerism. So we'll look into this explanation in the next lecture as well, but let me write down all the documentation that I need to explain in the next lecture. Okay, and if the number of pi bonds are odd in cumulene, then the terminal carbon valencies lies in the same plane, and it can show geometrical isomerism. So if number of pi bonds are odd in cumulene, then terminal carbon valency are in the same plane, and it will show geometrical isomerism. So in the next lecture I'll be delving more into the explanation part of whatever I have wrote in this lecture. So till then, good luck and goodbye.